Alright, let's get back into chapter 2. So we're starting section 2.5, measures of the center of data. So we have a couple of terms to define here, and then we're going to start looking at some numbers. So we're going to define the difference between a parameter and a statistic. So a parameter is a descriptive measure of a population, whereas a statistic is a descriptive measure of a sample. So we saw this back in chapter 1, but again we have that mnemonic device. So a parameter is for a population, and a statistic is for a sample. Okay, so when we're working with these values, they're going to look the same and be calculated almost exactly the same in most cases, but we do need to distinguish between the two so that we know whether we're talking about the entire population or just one sample out of the population. So the first thing we're going to talk about is the arithmetic mean of a variable. So this is the one that we typically think of when you hear the word average, right? You think of average, you typically think of the mean. So we have the arithmetic mean, either the population mean or the sample mean. Now the good thing is that they are calculated the same way. So the population mean is calculated by taking all of the values, adding them up, dividing by the total number of occurrences, and the sample mean is calculated the same way. So you take each value, add them up, divide by the size of the sample. The difference is a variable. So for the population mean, we use this Greek letter mu. So it's like mu is how we pronounce it, or like a cow, like moo. But it looks like kind of a curly M. So that's mu. That's what we use for a population arithmetic mean. Whereas for a sample mean, we use x bar. So this is just an x with a little line over it. So that's x bar. That's what we use when we're dealing with a sample. Okay, but again, they're calculated the same way. So let's look at an example. So the following data represent the travel times in minutes to work for all 7 employees of a startup web development company. Compute the population mean of this data. Round your answer to the nearest nearest hundredth. So we're dealing with a population mean here. So we're dealing with mu. And how we compute that is we take each value, add them up, divide by however many there are. So we have 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43 divided by, there are 7 data points there. And that, if you run that through a calculator or just do it by hand, you get approximately 24.86, and the units were in minutes. So we say the mean travel time for this population of 7 employees is approximately 24, almost 25 minutes. Okay, now you can see, obviously, none of them actually had a travel time of 24 or 25 minutes, right? One was a 5, one was a 43, but when you average them out, when you take that mean, you get that central value. Okay. So still using that same example, it says use your calculator, so we can use technology here to take a simple random sample of 3 employees, compute the sample mean, obtain a second simple random sample of 3 employees, again compute the sample mean, round each answer to the nearest hundredth, state any observations you can see from the population mean and the 2 sample means. Okay, so we're asking for a couple of different samples here. So we're going to get one sample mean and another sample mean, and we're going to see how those vary from the population mean and from each other. So what I'm going to do for this one is I'm going to use Excel. So you can use, like it said, you can use a calculator, you can use different softwares to do this, but Excel is pretty quick. So, and I've shown you guys this function before, but you just use the, oops, you have to type equals first. So equals rand between. So that's a random number between 2 values, and I want between 1 and 7. Okay, so I'm going to go ahead and actually do that. So I'm going to pull up Excel here. There we go. Okay, so I can go ahead, equals ran between 1 and 7. And you can see there it pops up with a number, but we want a sample of 3. So I'm going to go ahead and just get 3 of those. Okay, so we have 2, 4, and 5. Okay. So what that's telling us to do then is take the second person, the fourth person, and the fifth person. So that's 2, 4, and 5. So 36, 18, and 5. That's going to be our first sample. So 36 plus 18 plus 5 over 3. And let's go ahead and get the other one. Let's try to get some different numbers in here. Let's see, let's cut those. Paste in there. Okay, so we got a duplicate. If that happens, then you can just get it again. There you go. Yeah, every time you refresh it, it pops up with different numbers. So it is truly random. So we got 1, 3, and 6. So that means first person, third person, and sixth person. So that's going to be 1, 3, and 6. There could have been some overlap, and that would be fine, okay? Because there can be some give and take there. But just wanted to see some different values in there. So 23, 23, and 26. Over 3. Okay. And then these values, so we get 36 and 18 is 46, 54 plus 5 is 59. So we get 59 over 3, that's going to be 1, 29, that's 9.67, so 19.67. And then this one, we get 46 plus 26 is 66, 72 over 3, which I believe goes evenly. That's 224. Yeah, 24 even. All right. So if we look at these two sample means, we can compare these to the population mean. The second one is actually pretty close, right? It's only 0.86 off. The first one is a little bit lower. That's because it incorporated the 5, right? So you can see how getting different samples results in getting different sample means. This is why we have to distinguish between the two, because the sample means are all different depending on which people you grab for your sample. The population mean just is what it is. That covers everybody. Okay. Next up, it's asking for us to determine the median of this data set. So we're just going to rewrite it in numerical order. So we have 5, 18, 23, 23, 26, 36, and 43. Okay, so we have 7 values here. So I'm going to go in 1, 2, 3, 4. Right? So go right into the middle. So there's 3 on this side, 3 on this side. This is the middle value. So the median is 23, and that's a capital M, not a mu. That's just a capital M for median. Okay. Now, suppose that in this example, the startup company hires a new employee. The travel time of the new employee is 70 minutes. Determine the median of the new data set. So, for our new data set, we have all the same values, but we added a new one. So 5, 18, 23, 23, 26, 36, 43, and 70. Now when we're looking for the middle, we now have 8 data points. So I go 1, 2, 3, 4, 1, 2, 3, 4, and we're right here in the middle. So I have to take the mean now of the middle 2 values. So 23 plus 26 over 2 is 24.5. So that's the median. And just so you're aware, the new population mean of this is 30.5. So notice what happened when we introduced that new value. The median went up 1.5. The mean went up almost 6 units. Okay, and this is not a coincidence. Okay, and this actually brings us to our next topic. So now we have the same scenario, but suppose that they hired a new employee that has a 130-minute commute. I have no idea why they're commuting 130 minutes to work. Just find something closer. But how does this impact the value of the mean and the median? So you do the same thing we just did with the 70. The median would still be 24.5. The mean, however, would be 38. So why is this? Well, the median is what we call a resistant statistic. Okay? Median is resistant because it is resistant to change. Okay, it didn't matter whether we added 70, whether we added in a 130, whether we added in a million, whether we added in a 2. It didn't matter, okay, because the only thing that matters for the median is where the middle number is. And the middle number is dependent on how many values there are, not what the numerical value is. Okay, so we could have added anything else into this list instead of 130, and the median would still be that, 24.5. The mean, however, is not resistant. Okay, so the mean is not resistant. So let me make a note of this. So the median is resistant. The mean is not resistant because the mean depends on the specific value that we get from the data. So if I add in a really large number or an outlier, the mean is going to change significantly, but the median will not. Okay, so median is resistant, the mean is not resistant. Okay, and then we have the third kind of major value we talk about, that's the mode. So the third central tendency is called the mode. The mode can be computed for either quantitative or qualitative data. So the mode is just the variable, is just the most frequent observation. Okay, so the variable that occurs the most is the mode. It is possible to have no mode. Okay, so if you have every data point shows up exactly once and there's no duplicates, then there's no mode. Okay, if we have one number or one value that shows up more than the others, that's the mode. If you have two values that are showing up more than all the others and they show up the same amount, they would both be considered the mode. They share that title. Okay, so let's look at this example. So what is the mode for the weights of 10 students in the nutrition class? Well, we have 95, 117, 210, 154, 193, 117, 130, 133, 268, and 145. 117 got repeated twice. All the other values only occurred once. So that means the mode is 117 pounds. Simply because it occurred more often than the other values. Okay. For this example, find the mode color. So the mode color is the one that occurs the most. So let's go ahead and go through this list. So I have a red, 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 red. Okay. And then I've got blue, 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 blue. And green, 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 green. Okay, so let's tally these up. How many reds do I have? I have 5 reds. Blues, I have 5 blues. And I have 4 greens. So, what is the mode of this data set? The mode is blue and red. Okay, because they both occur more frequently than any of the other colors, in this case green, and they both occur the same number of times. So they share the title of the mode. Alright. Now we're looking at computing a mean using a frequency table. This adds kind of an extra layer into it. So when we're computing x bar, that sample mean, you can write them out if you want to. So this weight occurred, so 85 pounds occurred 4 times. You could go 85 plus 85 plus 85 plus 85 and do that for all of these, but that becomes tedious and it's really unnecessary. Instead of writing them all out, we're just going to do some multiplication. So I'm going to have 85 times 4, because it occurs 4 times, plus 98 occurs twice. That's the same thing as adding it together twice. Plus 100 only occurs once. Okay, plus 110 times 4, plus 115 times 3, plus 138 times 2. And then we need to divide by the total number of occurrences, right? The total frequency. Well, to do that, we just add up how many there are. So that's going to be 4 plus 2 plus 1 plus 4 plus 3 plus 2. Okay, and obviously these numbers are way too big to try to do it all by hand, so we'll just plug it into a technology, and we get out 106.0625 pounds. Okay, so the mean weight of the models in this sample is about 106 pounds. Okay, so when dealing with the frequency table, we can utilize the multiplication to simplify our work a little bit. Now, what about calculating the mean of grouped frequency tables? Okay, so if we go back to the textbook example, right, we looked at the costs of textbooks. We want to find the sample mean and the median of this. We're going to do exactly the same thing that we were just doing before. So I'm not going to go through all of that, but if you want to try it for practice, by all means, you get 299.58 for x bar for that sample mean, and the median, the middle value, is 307.50. Okay, and you can go back and look on the previous pages to find that example again. Okay, so that brings us, oh, and I should mention, you can also do this on Desmos as well. So finding the mean of a data set, finding the median of a data set, that's all stuff that you can do on Desmos using the same techniques, those functions that we saw before. So that brings us to 2.6, probably the shortest section in the entire the entire class. So skewness and the mean, median, and mode. So a useful way to describe a variable is by the shape of its distribution. So after we draw like a histogram, stem and leaf plot, whatever it may be, we want to look at how the shape is of that distribution, right? How is it grouped, right? Are the data values all very low, all very high, towards the middle? Are they all about the same? So there are some common distribution shapes here, and these are the 4 types that we're really going to be working with this semester. There's the uniform distribution, where the values all tend to occur with the same frequency. So uniform distributions pretty much look like a horizontal line on the top. Okay, so that's uniform. Then we have the bell-shaped distribution. That's going to be the most common one that we're going to work with. So bell-shaped because it has this, it looks kind of like a bell, right? That's the thing. So that's a bell-shaped distribution. Those we're going to be able to work a lot with. When it comes to the mean, median, and mode, okay, most of the values fall in the middle, and the frequencies tail off to the left and right. It has symmetry, right, between the 2 sides, relatively. And the mean and the median and the mode should all be the same. Okay. Then we have a skewed right distribution here, where all of the values are grouped to the left. Now, you have to, when you're thinking about skewing data like this, it's kind of opposite of what you would think. You have to think about it kind of backwards. So if it's skewed right, that means all the data is on the left over here. The reason we call it skewed right is because the tail is off on the right. Okay, so this is when the distribution is not symmetric and the tail to the right is longer than the tail to the left. So the mode is bigger than the mean, which is bigger than the median. Okay, and then we have, conversely, a skewed left distribution. This is when it's not symmetric and the tail to the left is longer than the tail to the right. So again, a skewed left distribution, all the data is on the right. Okay, so kind of backwards of how you would think. And then the mean is less than the median, which is less than the mode. All right. So that's it for 2.6. So just a nice short section just introducing us to those types of distributions, those shapes that we're going to be working with later on in the course. Now we get to measures of the spread of the data. So we looked at measures of central tendency, so the mean, median, and mode, right? Different ways of looking at the middle of the data. Now we're going to look at how spread out the data is. So we're going to start off just talking about the range. So the range is the difference between the maximum value and the minimum value of the data set. Okay, so the range is max minus min. Okay, and that tells you how widespread it is. So in this example, we have peanut butter jar prices, find the range of the data set. So we find the highest value, and we find the lowest value. And the range is just going to be the difference between those. So $3.99 minus $3.29 is 70 cents. Okay, so the range of this data set is just 70 cents. So that means that all of the values fall within 70 cents of each other. Okay. Now we come to the standard deviation. So standard deviation is a measure of variation based on how far each data value deviates or is different from the mean. Okay, so we're looking at how far away data is from the mean. The standard deviation has a few properties to take note of. It's always positive. It's 0 if all the data values are equal, right? So if all the data values are exactly the same, there is no deviation. They're all exactly the same, so the standard deviation is 0. If the data gets more spread out over a much wider distance, the standard deviation is going to be much larger, because there's higher deviation. It has the same units as the original data. It can be highly influenced by outliers, like the mean, so it is not resistant. And it is interpreted as the average is the mean, give or take the standard deviation. So we generally use this when we're talking about like margin for error. This isn't exactly how we get margin for error, but that same idea of this is the middle, give or take a little bit on either side. Okay, so when it comes to computing standard deviation, there is a slight difference between the population standard deviation and the sample standard deviation. So population standard deviation is abbreviated using lowercase sigma, so it looks just kind of like a little, I don't know, it's a little like a weird looking 6 kind of tipped over on its side. It's a Greek letter sigma. It's like a lowercase s. And this one is computed by taking each data point minus the mean, square it, add all those up, divide by how much data there is, and then take the square root of that whole thing. Okay, so it's kind of a rough calculation. We're not going to compute standard deviations by hand for very large data sets. That's just not practical. It just takes way too long, and the technology is so much faster. Then the sample standard deviation is just abbreviated using S. Okay, and this one, you do the same thing, so you take the data point minus the mean squared, add all those up, and this time you divide by n minus 1. So it's the number in the sample minus 1. Okay, the reason you take the minus 1, it mentions down here, is because of the degrees of freedom. Because the first n minus 1 observations have freedom to be whatever value they wish, but the nth value has no freedom. It must be whatever value forces the sum of the deviations about the mean to equal 0. So don't worry too much about the degrees of freedom. We're not going to deal with that much. Just so you're aware, that's the reason why there's a difference between these two, because when you're dealing with a sample, you only have so much leeway that you can give, whereas the entire population, you just take the whole thing. So that is our standard deviation. So in order to calculate standard deviation, we find the deviation for each data point, so data value minus mean. You square it, add those up, divide by either the size of the population or by n minus 1 if it's a sample. Okay. If you're not sure, so this is a good note right here, if it's not sure whether it's a sample or population, assume that it's a sample. That's always safer to just assume that it is a sample and compute the square root. Okay, so this is our step-by-step process here. So let's look at an example. So the value in step 4, which we'll touch on this a little bit, but that's called the variance. The variance is just standard deviation squared. Okay, so it gives us other information similar to the standard deviation, but that's what it is. It's just called the variance. Okay, so let's look at this example. So find the standard deviation and variance. Use the table to organize your calculations. Interpret the standard deviation in context of the scenario. So the mean value of all of these, you just add them up and then divide by 5. There's 5 data points there. That value is 3.682. It's going to be the same for all of them. Okay. Once you have that, then that leads us to the next part of the calculation. So data value minus mean. So we take this one minus this and just do that for all of them. And that's going to give us the following. We get negative 0.392, negative 0.092, 0.068, 0.108, and 0.308. Once you get each of those, data value minus mean, square it. So here you would need to use a calculator to get this. But we get 0.15367, 0.00846, 0.00462. Okay, notice that as we're further away from the mean, the standard deviation goes up as well, or these individual values go up, which will then in turn cause the standard deviation to go up. Then we get 0.01166, 0.09486, and then add all those up. So you add all those up together, we get 0.27327. So we're looking for sample variance. That's s squared. And sample standard deviation. That's just s. Okay, so the sample variance is just standard deviation squared. So basically just don't take the square root. So we get 0.27327 over number in the sample minus 1, so over 4. And we get 0.06832. That's our sample variance. And the standard deviation is just the square root of that. So square root of 0.27327 over 5 minus 1. That is 0.26138. Okay, so that tells us that in this example, the standard deviation is 0.26 cents. Okay, so one standard deviation away from the mean. And we're going to look later in the section at what this really tells us, but it tells us how spread out the data is. Okay, so we know that the mean is about $3.68, right? $3.68, give or take 26 cents on either side. Okay, so and again we'll talk more in just a little bit about what that looks like visually. Now for calculating standard deviation of a frequency table, so for this one we're not going to go through this entire process because you do it exactly the same way that you did before. Let me just show you one. So x bar, if you find, we got that earlier, right, just a couple examples ago. The mean is 106.0625. Make that thinner. 106.0625. Okay, and then you would take data value minus mean, so 85 minus 106.0625, so that's going to be negative 21.0625. Then we have to take into account that this data value of 85 repeats 4 times. Okay, so we would then need to take data value minus mean and square it. Okay, so data value minus mean is squared, so 21.0625 squared is 443.6289. Multiply it because that occurs 4 times, and that gives us 1774.516. So try not to get too caught up in all these numbers. I know this looks really complicated because it's got a lot of decimals in it, but the mean we found earlier. The data value minus mean, just subtraction, square it, multiply it by 4. That's all we've done. And then do the same thing for each of those, which again, I'm not going to take the time to do that because we're going to actually use the technology for this one. So to get the standard deviation of this sample, we would take the square root of each of those values, so 1774.516 plus etc., over the total frequency minus 1, so 4 plus 2 plus etc. minus 1. I can tell you if you were going to add all those up, you would get 4282.939 over 16 minus 1, which is approximately 16.898 pounds. Oops. Pounds. Okay, so the standard deviation of weights in this example is almost 17 pounds. Now let's look at how we can do that. So they give you the table down here for the TA8384. On Desmos, we can do this. Oops. Okay, so let me... waited too long, my data set went away. Here it is. Okay. So this data set we were already working with up here. That's the weight data set, right? 85 with a frequency of 4, 98, 98, 100, etc. So all we have to do, you can type it or just go to the functions. But you'll notice too there's one here that says STDEV, that's standard deviation. So there's also one you'll see down here that's standard STDEVP. That would be if it was a population. This one, however, is not a population. So we want the standard deviation of W. And we get approximately 16.898. Which is exactly what we had before, but all we had to do was create a 16-element list and then just type in that function and then we're done. So much faster to do it that way. So generally speaking, like I said, you might have to do it by hand for like a small data set, like 3, 4, 5, with small numbers, but big stuff like that, we're going to use technology to do it. So, all right. Next up, so this is something that we're going to talk about now, and then it's going to go away for a little bit and come back with a vengeance later in the semester. So this is calculating and interpreting z-scores. So a z-score of a particular data point is the number of standard deviations away from the mean given by this formula. So it's the data point minus mean over standard deviation. That gives us z. Okay, data point minus mean over standard deviation. This tells us how far away we are from the mean in terms of standard deviations. Okay, so the z-scores are unitless and are efficient values to compare statistics from different distributions. So the nice thing about a z-score, no matter how big or small your data is, the z-score will give you a number that tells you something about that data, and it's consistent. It's consistent across all data sets. So let's look at this example. So a mean score on a test for a statistics class was 82 with a standard deviation of 7 points. If a grade A is 93 points, what is the z-score for an A on the test? So we're going to take the data point, 93, minus the mean of 82 over standard deviation of 7. This is approximately 1.57. So what does this tell us? Well, this tells us that a person who scored a 93, right, got an A on this test, is 1.57 standard deviations above the mean. So, and if you think of a standard deviation as being just what it sounds like, standard, right, 1.5 is pretty high, right? It's not overwhelmingly high, but I would say that's significant, right? That somebody scored 1.5 standard deviations above the mean. Okay. Now let's look at an example in another context here. So student Pat was done taking midterms. She received a grade of 82 on her statistics exam, where the mean grade was 74 and the standard deviation was 12. She received a grade of 72 on her biology exam, where the mean was 65 and the standard deviation was 10. And she received a grade of 91 on her kayaking exam, where the mean was 88 and standard deviation was 6. And the question is, in which class did Pat relatively score better? Okay, so we know obviously her highest grade was in kayaking, but if everybody in kayaking got, a 93, she's actually doing worse than the class, right? Whereas if she got she got a 65, or excuse me, she got a 72 on her bio test. If everybody on the bio test scored a 40, then she's doing really well comparatively. So let's get the z-score for each of these. So we're going to get a z-score for statistics, a z-score for biology, and a z-score for kayaking. Alright, so we do data point minus mean over standard deviation. So 82 minus 74 over 12. We have 72 minus 65 over 10. And 91 minus 88 over 6. Okay, and then run these numbers. We get 0.67, 0.7, and 0.5. So what do these tell us? Well, this tells us that in her statistics class, she scored 0.67 standard deviations above the mean. In her biology class, she scored 0.7 standard deviations above the mean. And in kayaking, she scored 0.5 standard deviations above the mean, so half a standard deviation above. So which one did she score relatively better in? That would be the biology class, right? Because compared to that mean, given the standard deviation, she scored relatively higher than the rest of the class compared to the others. So she scored relatively higher in biology. Okay. So again, that's really all we're going to do for now with the z-scores, but we will be using them a lot in future chapters. So just keep that in the back of your mind. And then we come to the empirical rule. The empirical rule is really what helps us understand what the standard deviations tell us. So the empirical rule states that the percentages of data in a normal distribution within 1, 2, and 3 standard deviations of the mean are approximately 68, 95, and 99.7%. So what does that mean? It means that in a normal distribution, so a bell curve, 68% of the data is going to lie within 1 standard deviation of that mean. 95% is going to lie within 2 standard deviations of the mean, and 99.7% lies within 3 standard deviations of the mean. So in other words, if you score more than 1 standard deviation away from the mean, that means 68% of people are in here, plus however much is down here below, which we can calculate. Okay? But that means you scored pretty high, pretty far away from the mean. Okay? So this gives a real context. If you are more than 3 standard deviations away, that is insanely high. Okay? More than 3 standard deviations away means almost all the data is below you, statistically. Okay? And then similarly, if you are less than 1 away from the mean, somewhere in here, then that's relatively close, right? That's not particularly far away from the mean. Okay, so these numbers will help us in computing how many standard deviations away, how much data there is, beneath you or above you. It can help us with percentiles, all the stuff we've been talking about in these sections. Okay, so you can see the notation down here. Right, this is the mean plus no standard deviations, the mean plus 1, 2 standard deviations, 3 standard deviations, and then minus on the other side. Okay, so we count up and down by standard deviations on this graph. And then related to the empirical rule is Chebyshev's rule, also called Chebyshev's inequality. This states that the percentages of data in normal distribution within 2, 3, and 4.5 standard deviations are approximately these values. Why are those values less certain than the empirical rule? Because the empirical rule only holds if the distribution is bell-shaped, but Chebyshev's holds regardless of the shape. So Chebyshev's is less certain than empirical rule, but it applies to more types of distributions, not just bell-shaped. So it's up to us to determine which is more appropriate for the situation. You can always use Chebyshev's, but if it's bell-shaped, empirical rule is going to be more accurate and more useful for us. So, and that brings us to the end of Chapter 2. So great job working through. We had 7 sections in this chapter, so I know it's a lot to go through, but we made it to the end. When we come back in Chapter 3, we're going to start talking about probabilities. And start getting into that section of our course. So that's all we have for today. So I will talk with you all when we are in Chapter 3.